When providing assistance to individuals while they're lying in bed, nurses and human caregivers frequently and easily manipulate blankets and sheets over the body. Clearly, for robotic caregivers to be effective in such scenarios, they too must be capable of dealing with the obstacle that blankets covering the body present. In this work, we propose a new, graph-based dynamics modeling approach for targeted bedding manipulation. This approach, which we call robust body exposure, or RoBE, involves first capturing the pose of a person and a point cloud of the blanket that is covering them. We feed this information into an optimization loop where we find actions to uncover a given target limb by optimizing over a cloth dynamics model. Once the optimizer meets termination criteria, the robot then executes the optimized action. Our graph-based dynamics model inputs graphs that are composed from a voxelized 2D point cloud of an initial blanket state. The input graph has nodes that encode the 2D position of a point in a voxelized point cloud and edges that are formed between neighboring nodes. A candidate action that manipulates the cloth is represented as a global vector of the graph. We represent actions as 2D grasp and release points that the robot moves between linearly. We learn a dynamics model of the blanket using a graph neural network that, given a graph of the cloth's initial state and a perturbing action, predicts the displacement of the cloth, from which we can then compute the predicted final cloth state. We train our dynamics model on simulated data from executing 10,000 random actions to manipulate a blanket over a capsulized human model lying in a hospital bed. Our trained dynamics models can then be used to quickly optimize for actions that uncover target body parts without exposing other parts of the body. To assess whether a particular part of the body is covered or uncovered, we represent the human body using a set of points distributed evenly over its surface. We define an objective function that facilitates targeted bedding manipulation, using reward terms for uncovering target points on the body and penalties for uncovering non-target points, along with a few other penalty terms. We optimize the objective function over the dynamics model to find targeted actions that uncover the body. The RoBE framework has several key advantages. Namely, since only the cloth dynamics model is learned, we have significant flexibility to modify the optimization loop and objective function at runtime. For example, we can modify the action space based on situational constraints, scale terms of the objective function to change the priority of rewards versus penalties to get different outcomes, or add new targets to uncover, all without retraining any models. We demonstrate some of these advantages and compare RoBE to reinforcement learning and geometric baselines in a real-world evaluation using a mobile manipulator to uncover a medical mannequin lying in a hospital bed. While RL struggles to even learn how to complete the task and the geometric baseline has limited capacity to generalize, our approach has strong performance uncovering the mannequin. In a human study with 12 participants, we also demonstrate the effectiveness of our simulation-trained models in manipulating bedding over real people. In the first phase of the study, both the participants' pose and the target limb to be uncovered are predefined. We see that performance is generally consistent between participants, indicating RoBE's robustness to body shape variation. In the second phase of the study, the participant is asked to assume a supine pose of their choosing, and we uncover a random target limb. Here, we observe RoBE's performance subject to a diverse set of poses and body shapes. With this increased pose diversity, we observed some errors where the robot failed to complete a given trajectory by, for example, prematurely dropping the cloth. However, we overall observe strong performance uncovering most target body parts despite challenging variations in real human body shape and pose.